of our ATAL FDP on high performance computing and its applications. So we have our guest expert speaker for day 2, Dr. Rajesh Duriya from NIT Raipur. So Dr. Sridevi would introduce the expert speaker now.
Good morning, everybody. I am glad to introduce you all to Dr. Rajesh Duriya sir from Department of Information Technology, National Institute of Technology, Raipur. He is a PhD from IIT Allahabad, MTech IT from IIT Allahabad, BE IT from MITS Gwalior. His areas of interest include distributed computing, cloud computing, AI, robotics, soft computing, network security, quantum computing, and high performance computing. He has an array of journals, mostly in the spectrum of cloud computing, distributed computing, and high performance computing. To his bag, I would say very important projects he has carried out in next generation tech agriculture for vulnerable tribal community in Chhattisgarh state with a funding amount of 25 lakhs. Project duration was around 12 months. Another important project, funded project in welding robo for industrial applications. He has been in the member of board of studies. He has supervised more than 9 scholars, PhD scholars, more than 12 MTech students, and he supervised 45 plus BTech graduates. He has organized several international conferences, short-term training programs, also organized ATAL-sponsored workshops. He has delivered more than 20 expert lectures. He has chaired many international conferences. I would like to extend a hearty welcome to our resource person, Dr. Rajesh Duriya. Over to Anish.
Now I would request our HOD ma'am, Dr. S. Krishna Devi ma'am, to felicitate our guests for the day. Thank you, ma'am. So I would hand over the session to Dr. Rajesh Duriya.
So can I put my laptop?
Yes, sir.
So, very good morning to all. It's really a great honor and privilege for me to be here, and I would really like to extend my sincere thanks to Dr. Prasanna Devi Madam, who is the HOD of this institute, and Dr. Bharti Ma'am, who have really shown their real interest to have me here. So thank you, ma'am. Thank you so much for that. And in today's session, I am going to cover the introductory part of parallel computing And apart from that, I am also going to cover the introductory part of the HPC architecture and related systems. So these are going to be the basic may I have the pointers if possible?
Yes, sir.
So before moving further, I would really like to know that what you guys have studied in yesterday's session so that the things do not get repeated.
Basics of supercomputers. An introduction to quantum.
Introduction to quantum and basics of supercomputing. Okay, fine. And how many of you are students? Just scholars. Okay. And the rest are the faculties, right?
Yes, sir.
Okay. And how many of you do teach parallel programming in your courses? None? Okay. In that case, this session is going to be very interesting. Okay. Fine. So let us first start by understanding, I guess, this slide or this first computer detailing you have seen in the yesterday's session. So anyway, let me remind you once again. Now we are talking about ENIAC, which is the Electronic Numerical Integrator and Computer. It has been the first programmable electronic general purpose computer invented in 1945. The things have been studied quite earlier, but it got recognized in 1945, and it was designed by these two personals, John Mucci and J. Vesper Eckert. I don't know whether I am pronouncing correct or not, but anyway, so these two persons were responsible to design this big first computer, which were taking the help of vacuum tubes to build this system. And the interesting thing regarding this supercomputer was, or this first computer was, that it was designed to calculate the trajectory of the artillery shells, because in the World War II the people were not able to calculate the trajectory, so that the damage which they should have to the enemy, that damage was not being reflected. So to do that, to do all those sort of calculations, so what can be the projectile, so that the bomb they can bomb the enemy's tanks and the other things with a much more accuracy. Now if we talk about what is there in this first computer, so this computer has got a number of vacuum tubes. So in order to have a single decibel number, it requires a bank of 36 vacuum tubes, and with 10 such banks form a single accumulator. And in order to have the other timing and control mechanisms, we have to have some more additional tubes. Then we can have these features. And in total, ENIAC was comprised of 18,000 ENIAC was comprised of 18,000 vacuum tubes and could complete 350 multiplications in just 1 second. That was the speed of this first computer at that time. And then ENIAC was publicly unveiled in Feb 1946 through the patent for ENIAC, claiming among hundreds of other things to be the first computer, which was filed in June 1947, over a year after the public release of the product. And you will be quite amazed to know that in this particular first computer, number of female researchers were involved. So basically, you can give the credit for the designing of this first computer to the number of researchers who were female. Now you can see where the researchers are trying to build this supercomputer, this first computer. So this was so big because the size of vacuum tube was quite large enough. So that's why the size of these systems happen to be large.
Hello and welcome to History Pod. On the 15th of February 1946, ENIAC, the world's first programmable general-purpose electronic digital computer, was formally dedicated at the University of Pennsylvania. 18 months after entering the Second World War, the United States Army Ordnance Corps Research and Development Command agreed to fund the construction of a machine to compute values for artillery range tables. They approved a design by John Maudsley and J. Presper Eckert from the University of Pennsylvania, who began to build the enormous computer in secret in July 1943. Sited in the basement of the university's Moore School of Electrical Engineering, the enormous machine consisted of 40 panels arranged in a U-shape around the walls. These housed tens of thousands of vacuum tubes, resistors, capacitors and relays that consumed 150 kilowatts of electricity while creating so much heat that the computer needed its own air conditioning system. Nevertheless, it was able to complete up to 5,000 mathematical calculations per second. This made it possible to solve multiple complex problems each hour, whereas even a skilled human could take a day or more for just one. ENIAC was programmed using a combination of a wired plug board and switches. These programs could take days to plan on paper, and while it often took even longer to input them into the machine, the electronic speed at which the finished program ran saved significant time compared to computers that were controlled by card readers or other mechanical input devices. Although work began on the computer in 1943, it wasn't fully operational until early 1946 and was formally dedicated on the 15th of February. ENIAC was soon put to use running calculations to help build a hydrogen bomb and continued to operate until 1955.
So I guess you would have got the idea how we have got our first computer, right? Now, in this slide, we can show the speed of supercomputer which we have got over the period of years. So initially, the speed was being measured in the terms of OPS, which is operation per second. Then later point of time, we have realized that in order to measure the real power of any system, it is better to identify that how many floating point operations that particular system is able to do, because that require actual computational power. So that's why after a certain point of time, the people have started measuring the speed in the terms of flops, which is floating point operations per second. So initially, as you can see, the speed was not that much, but after 1960, you can witness that quite advancement have been reported in the speed of supercomputers, right? And now, in today's era, we can have the speed of hexaflops, petaflops, petaflop, hexaflops, and etaflops. So that is the speed which now the guys are able to witness. So we have got the fastest supercomputer, that is Frontier, and that has got the speed in order of hexaflop. And in India, we have got several supercomputers, and the top speed of that supercomputer is in the order of petaflops. So this is how the power of supercomputer is being measured. So these are the number of units. So the supercomputer which India has have the capacity in petaflops, and the topmost supercomputer which we got in the world, named as Frontier, has got the speed in hexaflops. Okay, and apart from that, even now USA is planning to build one more supercomputer that is going to be 8 to 9 times faster than the current one, and that the name of that supercomputer is going to be, I guess, Discovery. Okay. And this we have discussed that the floating point operations per second is used to measure the performance of supercomputers, and generally the speed of any computing device, especially supercomputer devices, are being measured in terms of flops. And top500.org is a site that rank the supercomputers which are there in the world according to their capacity. So let's say we have got number of supercomputers, but how do we rank them? So for that we have a program called as HPL, High Performance Link Pad. So that program is being run, and in order to run that program, in order to run that benchmark, the planning has been, a real planning has been done well before in advance. So let's say first you need to put your request. First you need to put your request that you need to test the speed of your supercomputer, and then the number of people will come and they will run the benchmarking, and then thereafter they will measure that how exactly your supercomputer is performing the things. Okay. Now we have got two things. The first thing is called as RPEAK, which is theoretical peak performance, and the second thing is RMAX. Okay. So have you guys have the idea regarding RPEAK and RMAX? No? Okay. So as the full form itself says that it is going to be theoretical. So given the hardware, let's say you have got 4 cores or 40 cores or 40,000 cores. So given the speed, what is the theoretical base performance that particular system can give? That is called as theoretical peak performance or RPEAK. And what is the actual performance which you are getting while the system is running? That is called as RMAX. For example, the dial. And for example, you would have realized that in your mobile you have got 8 GB of RAM, 16 GB of RAM. But in actual, when you are using it, how much of GB or how much of RAM you are using it, or you are able to use it? Because some of its part is already being used by the operating system, right? Android operating system. So only few of the memory is available. Similarly, have you ever encountered where the whole 8 GB has been used or 16 GB has been used? Okay, so most of the time, even the same case or same example can be considered in your laptop. Have you ever encountered a situation where you are able to use all the computational power of your laptop? No, right? So that's where we measure that what is the maximum performance you have reached given the set of resources or which you claim that you have built. That is called as RMAX. Okay, theoretically it's different, but practically how much actually it has achieved. Okay. Now this is how we calculate the flops, and in this particular architecture we have got number of sockets. So whenever we talk about any computing unit, any compute unit, we have got number of sockets into that unit. So first we need to take care that how many sockets are there. And the moment we come to know about the number of sockets, then within a socket we may have number of CPUs. Okay, and the moment we have the number of CPUs and their respective clock cycles, so with that we can calculate the flops, when the speed is flops. So let's say you would have seen a motherboard. We will come to that in the coming slides as well. But for a moment, I would like to tell you that you might have seen a typical motherboard, right? In that motherboard, which you have got in your desktop, usually it has got only one socket where you put your processor. Okay, it is the place where you put your processor. So if you have got 2 sockets, that means you can put 2 processors. And usually that is the case when you use workstations. So in workstations you have got special chipsets, and those chipsets provide you the provisions where you can put multiple processors, because it has the provision of multiple sockets. So in multiple sockets you can put multiple processor, and within a processor you may have multiple cores, means multiple CPUs. For example, in your mobile you would have realized that you got quad core, hexacore, octa-core. That means you got a single processor, and in that single processor you got 8 number of CPUs. If it is octa-core, that is the case. Then you will be realizing that it has got a speed of, let's say, 1.5 gigahertz or 2.3 gigahertz. So that is the clock speed, right? So for any system, if you would like to calculate the speed in flops, then this is how you can calculate it. First, you need to find out how many number of sockets are there, and in a particular processor, how many number of cores are there, then what is their clock speed, and how many flops are being executed in a cycle. So the moment you multiply them together, you get the final speed. Okay, and how many flops per cycles are there, that you can get in the spec sheet of any processor. That you can get in the spec sheet of any processor. So that will tell you that what exactly or how exactly that implementation in flop per cycle is being implemented or has been implemented. Okay, so that FMA you must have to know, that is fuse multiply additor. That is the full form of FMA. So that will come with the spec sheet of any processor.
So we don't consider the core processor or accelerator while calculating this block.
This coming.
Don't we consider the performance of the accelerator or coprocessor and GPU while calculating these blocks?
No. As of now, this is straightforward, but the moment those things come into picture, because this is the case when we do not have any GPU, and the moment we have got GPU, of course, those things will come into picture as well. Okay, so we are just considering a case where we have got a straightforward motherboard where we got number of sockets, and we have put processor into those sockets, and each and every processor has got number of cores. Now the second scenario maybe, as the ma'am has said, what if we have got the graphical processor? So the moment you have them, because each and every graphical processor have got their own way of doing the things. So what we tend to do, we tend to compute their speed in a separate way. Okay, because the clock speed of those processors might be different. That is one case, and the number of processor in that case is going to be huge. So in typical CUDA cores, or if you talk about any graphics code, graphics card, then they may have around, let's say, 1000 number of cores, 1500 number of cores. Okay, so that is going to be quite large in numbers, and those cores are going to do very specific tasks, or you can say very minimal tasks in number. Because if you try to simply calculate the addition of two numbers, let's say 2 plus 5, a simple processor is going to do that. The task is simple. Okay, it is going to execute in no time. But what if the same task has to be performed 1 million times or 1000 times? Then again, the instruction has to be executed, the operands have to be faced, and the things has to be done. So that overhead is going to take a lot of time. That is the problem. Okay, and what CUDA cores does, or what graphics processor does, that in order to do these simple calculations, there is no need to have the full-fledged CPU or full-fledged computational unit. Rather, let's have the small ALUs which are able to do these small computations. Okay, and those number of processors are going to be huge in numbers in graphics processing units or in GPUs. That is the case. Okay, and that's where the image rendering and other graphical things are being done, because all those things are going to be represented in the form of matrix, and only those simple operations are being done using the graphics processor. Okay, so you have got several ALUs which are responsible for, let's say, some 16.14 operations. Okay, some 16-bit integer operation or 32-bit integer operations. So that's where the secret lies in graphics processor. This one? 24?
24 core divided by socket, right?
This is cores per socket. Number of cores per socket. Okay. So let me visualize you once again. We may have a system. Let's say just you can again visualize that motherboard. If one socket is there, then you will put one processor into it, and in a processor there can be multiple CPUs. So if you have got one socket, if you put one processor, and within that one processor you may have number of CPUs. So let's say if you have got 16 CPUs, then it is going to be 16 by 1. Okay, like that. Is that clear? This one? So if you got two sockets, then it is going to be 48. Now this is the performance development which has been observed over the period of years. So we have got three things over here. The first thing is the performance of a supercomputer ranked at 500 place. We have got number of supercomputers which have been developed by a number of countries. Now in this slide we are seeing the performance of some of the supercomputers collectively and standalone. So this is the performance of a supercomputer which has been ranked at the 500 position. Okay, that is the performance in blue color. And then in the yellow color we can see the performance of a supercomputer which has been ranked 1. That is the performance of that supercomputer. And then in the green color we can see the performance of all the supercomputers when their performance have been summed together. So this graph will tell you that there is not a huge difference. That means it is also going to state the power of the supercomputer which has been ranked number 1. Even though here you are adding the power of 500 supercomputers together, even that supercomputer is matching their power. Right? So if I remember correctly, then that fastest supercomputer has got around 9 million GPU cores. If I remember correctly, I am wrong. Okay, but around 9 million GPUs are there in the system. And it has the HPL of 1.1 exaflops. Now, the Galilei has gave us a very famous quote which says that mathematics is the alphabet with which God has written the universe. Right? Now, if we talk about the traditional way of doing the things, then how we do things? First, whatever is there around us, we try to observe that, and then we build the theory upon it. Then thereafter, we carry out the experiments, right? And then this process has been modified, where first we observe the surroundings, then we build the theories, thereafter we do the number of experiments, and then we validate those experiments with the help of some computation. The moment you have got data, then you do number of computation to find out the validity of that experiment. Okay. Thereafter, if we talk about what is computational science, so it is generally made of three fields: science, mathematics, and computer science. So first you create the mathematical formulations. Thereafter, you apply the computer science algorithms to solve those things, and these three things altogether form the field called as computational science. So you may have number of problems, and of course those problems are going to be defined in the mathematical expressions, and thereafter you need to have some good optimal algorithm so that the proper analysis can be done. And when all these three things come together, we have a field called as computational science. And nowadays we have got number of courses, number of degree courses which are running especially on this particular domain. So you might have heard that even the IISc Bangalore has got a very specialized department of computational science. That means they have got number of problems which are really complex in nature and they require a huge computation. Okay, so how that computation has to done, how the things have to be parallelized, those things are going to be studied. Now these are the some of the HPC applications in science. For example, atmospheric science, earth science, space science, life science, nuclear science, nanoscience, crash simulation, aerodynamics, structure analysis. So the most important thing and most common thing in all the applications is that all these applications are going to create a huge volume of data. When the volume of data is huge, when the possibilities are huge, that means you really need to have very powerful computers so that all the possibilities can be explored. If you talk about weather forecasting, then what is special in that? The special thing is we need to explore all the data. Okay, we need to analyze all the data in a stipulated time. If you are getting the weather information of today after 10 days, then it is of no use, right? So you want to have the information as early as possible, and to have that we do need these fast computers called as supercomputers. So let me repeat once again, the common point in all the applications is that they have got huge amount of data and they have got number of the huge exploration space. So you really need to have very fast computer so that all the possibilities are being explored. For example, in fluid dynamics, if you talk about what is the movement of a particular particle, then that particle may move in any direction, and with a small change in any parameter it may take n movements and all. So how to simulate each and every movement of that particle, and we may have millions, billions of such particles. So how to simulate the behavior of each and every particle. Okay. Similarly, in each and everything, for example, in crash simulation, what if the car has crashed, let's say some angle was different. Okay, if the car has crashed in the angle of 45 degree, then what will be the condition of the car if it has struck at, let's say, 45 at 44 degree, then what will be the result? What if the car has crashed at 40 degree angle? Then you need to explore each and every such possibility, and to explore such possibilities you need to have really fast computer. Okay, so in each and every such aspect, the thing is large volume of data is there and the exploration space is very huge. Okay, so that is the common point. Now let's see some of the basics of HPC. So we will start by having parallel computing. So first let us see how we can define a parallel computing. So a large collection of processing elements that can communicate and cooperate to solve large problem fast. So in this case we are going to have the number of processing elements, and those processing elements can communicate and coordinate in order to solve a bigger task. So that is the very elementary definition of parallel computing. So it states that we are going to have number of, not a single one, we are going to have number of processing units, and of course they are able to communicate with each other. And why that is needed? Because we may have a task, and in between we may need to interact in between the processes. That's right. Now we have got number of computing paradigms. We might have heard about these paradigms many number of times, right? So I feel that it is quite important to really know what exactly we mean by these computing paradigms and how do they differ from each other. Okay. So let's first see what is our distributed computing. So any one of you who can tell us what is the distributed computing? Now? Okay, now then let us move for the break. Then we will again assemble after the break. Just try to find it out in the system that how efficiently the existing resources are being utilized. Okay, the moment you know it, you will know that how many resources are just sitting idle or not being used. Then what you can do, you can have your program ready, you can run the profiler, and the profiler will let you know that your problem can be converted into a parallel program. Means there are going to be certain sections which can be executed in parallel. For example, in your program, there can be number of sections which can be executed in parallel. There can be number of functions that can be executed in parallel. There can be number of for loops that can be executed in parallel, because that for loop is going to have the number of iterations. So those iterations can be executed in parallel. So that will help you to run your code in parallel, because there are going to be certain segments, certain part, certain portion that can be executed in parallel. The moment you come to know, you will run those chunks in parallel and the efficiency of your program will improve. Okay, so that way you will be able to exploit the full potential of your HPC system or your workstation. So let's say if there are 42 cores, okay, and as of now, if you are straightforward running the program, then might be only 2 to 4 cores are being used. The rest are just sitting idle. Okay, so just by implementing these parallel programs, you can use all these units. Okay, so that will improve the efficiency of your program. And then just observe the performance, then see the result. Still, if you need the result in a much faster way, then you can look forward for some other systems. You can have the combination, and then you can look for the MPI programs and all. Okay, so if that doesn't solve your problem, then you can go forward for your HPC request and all. Okay. So that is the answer for your question.
So mine is like we have minimized all the data. So we have set aside about range so that we are keeping our data in a known space instead of infinite. So we are making more variables numerical registers. So we are trying to put that into a frame where we establish a range so that we don't have to go from start to the end. So that's how we made it.
That's programming logic. So that you need to ensure, because as a field expert, you know what exactly you want to carry out.
Yes. Now they are telling that remove all those ranges, let it run freely. So if I have to let it run freely, then workstation is not compatible to it. So now I have to switch the fixed standard to standard. So like I have to remove all the ranges which I have put for that, and I have to analyze the instabilities. So for that I need a HPC.
Okay. So the straightforward answer for your and every problem, first you need to know your problem. What are the dependent variables?
Yes.
Because you can execute the parallel code when the things are independent. Only then they can be run in parallel. If they have got some shared variables, then you need to identify that portion, those variables, and then you need to tackle those variables accordingly. Okay? So that is the answer, and for that you need to sit, you need to check the flow of the program, and you need to find out, okay, this is the portion that can be run in parallel, there are no shared variables and all. So that's why I am telling you, not on the whole program, not the whole program is going to run in parallel, rather the chunk of that program is going to run in parallel. So you need to identify that, okay, this chunk has got no shared variable, this has got straightforward for loops and number of iterations are there, and that has to be executed in parallel. So that you can do. So those small segments you need to identify. Okay.
It's like
And straightforward thing, whatever program you have got, just run it or have a profiler run to that program, and then you will find out the chunks and the segments that can be run in parallel. Okay. And some other things will be discussed in the second session as well. So now let us start what we mean by some computing paradigms, because we have got number of computing paradigms, and very often we come across these terms like distributed computing, parallel computing, mobile computing, and so on and so forth. So to begin with, first let us try to understand what exactly we mean by distributed computing. So any one of you who can tell me what is it? And let me tell you, all the computing paradigms except your quantum computing more or less is going to be the form of a distributed computing model. So this is superset, and all the other computing paradigms are going to be the subset of it. So we can define a distributed computing as a set of hardware or software components which may be partially separated, which are networked together to accomplish a task, and they communicate and coordinate using message passing. So the important thing which has to be noted over here is that we have got number of components, and those components can be software or hardware. That means, okay, we have got number of laptop or desktop, hardware components are there, fine. But when we are talking about software components, that means we may have number of programs. And the moment we have got number of programs, and if those programs are able to communicate with each other, if they are connected to each other, that means they are also forming a distributed system. Okay, so the important thing is they have got number of components, and those components are connected, and they are able to communicate and coordinate. So this is the very general definition, and whichever computing paradigm you observe, they are going to have this thing in common, right? And these are some of the characteristics of a distributed system, which are concurrency, no global clock, and independent failures. So the moment you try to realize any distributed system, so these are the things which will always be there. If you have got number of components, if you try to utilize the resources as much as possible, then of course you will be having a bigger task, and that bigger task has been divided into smaller tasks, and those smaller tasks are being handled by several number of components, and you expect those components to work simultaneously or concurrently. Right? Only then that particular concept is going to prove its utility. If you got number of components, then you expect all those components should work together, should work simultaneously, so that you can have your result in minimal time. Then no global clock, because in distributed system we do not have any notion or any mechanism through which you can determine the time exactly. Even your atomic clock has got some deficiency. That's a different thing that in 1 million years it is going to show you the variation of 1 second, but it is going to show you the variation, and that is the accuracy of that atomic clock. And again, in order to take that timing to us, we are going to have several mechanisms, and those mechanisms are going to have their deficiencies with them. Okay. Then independent failures. So the moment we have got number of components, then they may fail in a variety of ways. So that is also one of the concerns which will always be there whenever we talk about a distributed system. So your LAN setup is a typical example of a distributed system. Is that clear?
Yeah.
Then we have got the parallel computing. So the principle is, again, the large problems can often be divided into smaller ones which are then solved concurrently. And in this case, we solve a task by making simultaneous use of multiple processing elements. And while in case of distributed computing, we solve a task by simultaneous use of multiple processing elements, typically isolated and heterogeneous in nature. So the basic difference is between parallel computing and distributed computing. Distributed computing is a comprehensive solution or is a comprehensive paradigm, or it's a, we can say, umbrella under which the parallel computing or processing will come into picture. So in this case, the components, in case of distributed computing, the components may be placed at geographically separated locations. It is very much possible that one of the component of distributed system is placed in this lab and the other component is being placed in the other lab or in other college or in other country. While in case of parallel processing, the things are going to be placed at one, all the computing devices or units are going to place at one place. For example, in this laptop we have number of processors, and in that processor we have got multiple CPUs. So all those CPUs have been integrated to that processor only. So that environment is going to form the parallel computing environment. Okay, because even in that case we have got number of components, but all those components have been placed at one place. Okay. So a task can be divided into number of subtasks, and those tasks can be executed instruction wise by variety of CPUs. So that's how the parallel computing is being done. While in case of serial computing, a task again can be divided into subtasks, but it is going to be executed serially. Okay. Now these are some of the differences between the parallel systems and distributed systems. So if we talk about the memory management, then in parallel system we have got tightly coupled shared memory in the form of unified memory access and non-unified memory access called as UMA and UMA. While in case of distributed system, we make the use of message passing mechanisms and RPC, RMI and Corba protocol to have the memory access. And then if we talk about the control, then we have got global clock control in parallel systems, while the same is not possible in distributed systems because there is no notion of global clock. The moment we have got number of components which are partially separated, then having synchronization among those components is quite problematic, quite cumbersome. But if all the components are placed at one place, for example in your laptop you just talk about all the CPUs, then of course the speed is going to be more and the problem of synchronization is not going to be that much hectic, which has been the case in the case of distributed system. Now the main focus in case of parallel system is going to be scientific, while in case of this system it is going to be more or less the availability and reliability, and of course it is going to give you the advantage in terms of cost and scalability. So if you just talk about your IRCTC servers or infrastructure, then that is example of the distributed computing. Okay, and if you talk about your laptop, if you run any program using multiple CPUs, then that is going to be example of parallel computing in general. Okay. Now mobile computing, it is also called as nomadic computing, and it is the ability to connect portable devices to wireless enabled network to access data and services while on the move. So the definition itself tell you what exactly is going to happen in this sort of paradigm. So we have got mobile device and they do carry the computing capabilities with them, right? And we can perform the computing while on go. And of course it is useless to say that all of them are going to be networked through a wireless network. Then we have got ubiquitous, also called as pervasive computing. In this, what happens? It embeds computing capabilities into everyday objects so that devices can understand and anticipate needs without manual intervention. So it involves embedding tiny microprocessor in everyday objects to enable wireless communication between devices and people. It allows devices to automatically connect and share information. So we can think of any device, any type of device, even your AC or your wearable devices. So the moment they have got communication capabilities, if they have got a small amount of processing power, then they can form a network of devices, and together it can be called as an example of ubiquitous computing. Why ubiquitous? Because the variety of devices are there. Okay, variety of devices are there, and they can carry very basic infrastructure to connect with the network and to do some computations. Okay. Then we have got cluster computing, and in this setup what happens, we have got a set of computers that work together so that they can be viewed as a single system. Although it is a whole system altogether, but for the end user point of view, it is going to behave as a single system. How exactly your request is being served, that is not going to be known to the end user. Which compute node is exactly giving you the result, that is not going to be known to the end user. The end user is going to, okay, I just put my request and I got the result. Okay, if you are trying to book your ticket on the IRCTC server, then which node exactly is serving your request, you are never going to know. Right? And apart from that, unlike grid computers, computer clusters have each node set to perform the same task controlled and scheduled by software. So more or less, all the nodes in this setup are going to do the same type of job. Okay, they can do variety of jobs. Okay, but in cluster computing, all the nodes are going to do the same type of job. That is the important thing. And more or less, they are going to have the homogeneous node as well. The same sort of specification is going to kill by each and every component in this setup. Okay? For example, in your LAN setup, more or less you have got the system with same configuration. Right? And if they are doing the same job, then you can say, okay, this is nothing but an example of cluster computing. Of course, some cluster algorithms and some cluster protocols have to be followed. Then we have got grid computing, and one can define grid computing as a large-scale science and engineering application that are done through the interaction of people, heterogeneous computing resources, information systems, and instruments, all of which are geographically and organizationally dispersed. This is very important because at the last, so this is very important because a slight difference is there if we compare it with the dispute system, and that difference is that now we have included people as well. Earlier we were having a set of components that can be software or hardware, right? But now we have included people along with heterogeneous computing resources, even the information systems are there, even the instruments are there. So all of them together have formed a pool of resources, and they are going to be used for especially large scale science and engineering application. And that setup is called the grid computing. So the overall motivation for grid is to facilitate the routine interaction of these resources in order to support large scale science and engineering application. So there can be one application that is quite huge in nature, that requires a lot of computation. Even the fastest supercomputer is not able to do that. But we as a human being need to process that data. Then what to do? So can we think of a system where all the supercomputers can come together, where all the powerful systems can come together, where all the instruments can come together? Okay, where all the people who hold the capability to help the cause can come together. Okay, so the moment all of them form a group, that group is called as a grid, and that is the example of grid computing.
Any examples?
An example is there. You might have heard about this Big Bang experiment, if I remember correctly. Okay. So in that experiment, number of countries have come together, number of labs have come together, and number of scientists and instruments and information systems have come together, and they have formed a grid, and they have done this experiment. Okay. Many systems are available. So that's why this special thing is they are really designed for very large scale science and engineering application. Is that clear? Then we have got cloud computing, very fascinating term which we oftenly come across, right? So how do we define it? We define it as a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources that can be rapidly provisioned and released with minimal management effort or service provider interaction. The last, you have any doubt? So the important thing is, again, it is a model that enable ubiquitous. That means we may have variety of devices through which we can access the cloud resources. We can access the cloud resources with your laptop, with your mobile, with your desktop, right? That means it supports ubiquitous computing. You can access your Google Drive with your mobile. You can open Gmail with your mobile, with your laptop, with your desktop, and all those email services, Google Drive services, Box or Dropbox, all are cloud services. If you are able to access with number of devices, that means it is enabling ubiquitous environment. Then convenient on-demand network access. Convenient means whenever you want to access your storage or whenever you want to access your Gmail or Google Drive data, now you can do that. It is really very convenient, right? Just few touch and you are in there. Isn't it? And on demand, whenever you require. That's why. Whenever you require, you need to access your data, you can just open your mobile and you can get the access. Thereafter, to a shared pool of configurable computing resources. So number of computing resources have been placed at one place, okay, and that together form a resource pool, and that resource pool may be made of networks, servers, storage devices, applications and services. So they together form a resource pool, and we can access that resource pool with any type of devices or more with most of the devices very conveniently, and of course these are going to be shared. So if 10 people are trying to access, then depending upon the availability, that can be extended to the end user on sharing basis. For example, if I have got 100 number of computing cores and she has requested for 10, I will extend that 10 core to her, and if she has requested another 5 cores, so I will extend the 5 cores to her. That means the central pool of resources is being shared. It is not like all the 100 cores have been extended to her. However, she had the requirement of 10 core only. Okay? So whatever resources are there, that resource pool is actually being shared. Then can be rapidly provisioned and released. So that has to be available to the end user as quickly as possible, with the minimal management effort or service provider interaction. So this is how you can define a cloud computing, and this is the NIST view of defining the cloud computing. So we may have a variety of deployment models, for example, private cloud, public cloud, hybrid cloud, and community cloud. So whatever resources we have got, we can extend those resources in this type of model. So to means who can access those resources, whether those resources are being opened to some set of users or to the general users, or the combination of them, or to the enterprises who hold the common interest. That's where the concept of community cloud will come into picture. Okay, who hold the common interest, so that the cost sharing can be done. For example, if this is the campus and someone wants to open new campus, so what they can do, they can just have the MOU with the SRF that you run your campus in the noon time, in the daytime, we are going to run our campus in the night time. We are going to offer some diploma courses. So they do not need to build the whole infrastructure. They got the common interest that we want to also run some courses. So that way the cost sharing will be done. So that's how the community cloud will come into picture. Okay. Then all the resources can be extended in the variety of ways called as software service, platform as service, and infrastructure service. So these are some service delivery models. And this is how we can visualize the cloud computing model, where we have got number of devices which are trying to access the resources, and those resources can be extended in the variety of ways, like as a software service, whether platform as service, where you actually build the services and then you extend the services. While in case of infrastructure services, you have the raw hardware or the resources with you, and then you make the use of those resources as per your requirement. Okay. Now this is the difference in between grid computing and cloud computing. So more or less, grid computing talks about decentralized management, while the cloud computing is going to talk about centralized management. And apart from that, it follows the client-server architecture when we discuss cloud computing, and when we have grid computing, so more or less it is going to have the distributed computing architecture. So these are some of the things, and one more notable thing is the application type. So whatever data is there in the grid computing, that is being processed as a batch. You collect most of the jobs together, you form a batch, then in a single shot you put it for the computation. Okay. And while in case of cloud computing, it is more or less interactive. Whenever you want, you just get the things with you. Okay, that's why. Now, fog computing. So, fog computing is a decentralized computing infrastructure in which data, compute, storage, and applications are located somewhere between the data source and the cloud. So, all these computing devices are there, but they are sharing their data to some nodes which lies in between the actual cloud. So, rather than going to the actual cloud, which will give rise to the more latency, more communication overhead, there can be a number of applications where the data size or data volume is sufficiently small, and that data, if not being processed on the devices, then can be processed in between. Okay, so what will happen with that? The communication overhead will come down. For example, rather than sending the CCTV camera of each and every classroom directly to the cloud, can we have a central computing unit within the SRA which is going to analyze the data of all the CCTV within the SRA? Some basic data. For example, whether the class is going on or not. And if situation arises where we need to identify whether that person is there in the class or not. So that is going to have several phase cognition algorithms, right? So that is going to be some computational extensive task. So that task either can be offloaded to the cloud, and then cloud is going to carry out that algorithm. Okay. Then we have got edge computing. So in this case, more or less, the devices that carry some computational units with them, they can do some elementary processing. That's where the term edge computing comes. Okay, so that brings computation and data storage close to the source of the data. For example, is smart vehicles. the Google cars and all. So whatever data they are collecting, they are able to process that data on board. So they may have multiple sensors, multiple devices, and all those devices data are being collected at one place, and that place is taking care of all the real-time processing. Okay? In a car, there can be number of sensors, number of computing devices, right? And all those devices can send their data to one place, and that place is again on the car only. Okay? And they can do the processing. So if that is the case, that means it is an example of edge computing. Okay? Then the quantum computing, that is quite tough to understand, but as a layman I can tell you that it is nothing but a multidisciplinary field comprising aspects of computer science, physics and mathematics that utilize the quantum mechanics to solve complex problems faster than on classical computers. Apart from that, if you talk, currently no quantum computers can perform a useful task faster, cheaper or more efficiently than a classical computer. That is the answer of the question which we just asked. Okay, so there are going to be number of algorithms where your typical classical computers are going to be useful. It is not like if you build the quantum computer, then it is going to be useful for each and every application. No. Still your HPC system, your typical systems are going to be in use. Because not each and every problem has got a quantum solution. There are particular quantum algorithms, only those algorithms are going to leverage the advantage of quantum computing. Okay? So quantum advantage is the threshold where we have built a quantum system that can perform operations that the best possible classical computers cannot simulate in any kind of reasonable time. Okay? So more or less, examples can be applications. So if you know about Shor's and Grover's algorithms, so what happens? How exactly we search? How we search any element? Let's say in a tree. How do we search it? Top to bottom, and then we have got one approach. But what if we do the same thing parallelly in multiple dimensions? So if we are doing that, because quantum computing gives you the facility of entanglement and superposition, and that give you the flexibility of using more qubits. In moment you build or you have got the quantum computers of more qubits, then they will be able to give you more dimensions where you can increase your search space exponentially. And that is the beauty of quantum computer, because now you are able to have your search space increase exponentially, so that will going to give you the quantum advantage. If you have got 2 qubits, let's say 10 to the power 2, then what if you have got 10 qubits? Then just visualize the dimensions. In how many dimensions now you are able to search. So that's how, if you just come across the quantum computing needs, that the IBM has now built a quantum computer with 50 bits, then with 433 bits. So the more number of qubits, that means the more number of dimensions are there where you can parallelly do the thing. Okay, this is one way of saying things.
So, but how do you justify the second one? Currently, no quantum computer can perform a useful task faster, cheaper, more efficiently than a
Yes.
classical computer.
For example, you just need to add 2 variables A and B, and if you try to do the thing with the quantum computer, then the quantum computer is of no use. Okay, so the basic things, because the quantum computer will only going to help you out when you have got quantum algorithms to solve them. There are some particular methodologies or algorithms. If you have the algorithm or that problem, only then you can use it.
Then so far shows and drawings are the only one good. There are quantum
People are working, people are devising new algorithms, and if those algorithms are there, only then you can leverage the advantage of quantum computing, not for each and everything. Now we have got HPC. So high performance computing most generally refers to the practice of aggregating computing power in a way that delivers much higher performance than the one could get out of a typical desktop computer or workstation in order to solve larger problems in science, engineering or business. So, yes. So it makes use of parallel processing for running advanced application programs. Is a set of computing technologies for very fast numerical simulations, modeling, and data processing. Is employed for specialized applications that require a lot of mathematical calculations. Uses computer power to execute a few applications extremely fast. So these are the number of things where, or this is how you can define high performance computing. So in general, what happens in this thing is that you have number of computing elements or computing nodes, and those are connected together and they can form a single system collectively. Okay, and the moment you put your job into it, that job is going to be processed by the whole system. So how exactly that is going to be done, we will discuss in detail in the coming session. So, and how do we access it? We access it with the help of some dedicated compute node called as login nodes. So yesterday I guess you have learned it using SSH, how you were using that NIT 3G NIT 3G SSH you use, right? Param? So, a supercomputer is a system that performs at or near the currently highest operation rate for computers. Now, there is one thing. Okay, so now can I? The escape. This one? So, this is the shared memory models for multiple processor system, and we are going to see the exercise on this only, called as UMA and NUMA. UMA stands for Unified Memory Access, where all of the processors in the multiple systems use and access the same memory with the aid of the interconnection network. So you may have number of CPUs, okay, and all those CPUs are making use of the common memory. If that is the case, that means we have UMA in action. If we have got number of CPUs and many CPUs, if they have their own memory with them, and if they are forming a network, then that is an example of NUMA. So along with sharing their own memory space, they can access to the memory space of the other CPU as well. So if you got your system with you, right, and if you are running a program within that system, that means it is UMA. If you got multiple systems and that have been connected, and then you are creating a multi-processing environment, then it is going to form NUMA. Because each and every system have got their own memory space, and in between you need to have the multi-processing environment. So apart from using its own memory space, it is going to use the memory space of the other system as well for certain applications or programs. So that is an example of NUMA. And in COMA, that is cache only memory access, depending upon the requirement, the memory is allocated at the runtime. Okay, so local memories at each node are used as cache, and data partitioning is dynamic and implicit. Attraction memory acts as a large cache for the processor. So let's say if there are 4 processors and a huge requirement has come to this processing, so all the memory will be allocated to this one. So that is the example of COM. These are some of the differences in between UMA and NUMA. So UMA is going to contain a single memory controller and NUMA is going to utilize several memory controllers. Memory accessing time for each CPU in UMA is same, right? While it is going to be different in NUMA. It depends upon the distance of memory from the CPU. Thereafter, UMA utilized in a variety of general purpose and time sharing apps, while it is being employed in real time and time critical application. So these are some of the differences in between UMA and NUMA, and of course if you just talk about the memory access, it is going to be faster in NUMA. This is another way of looking the same thing, which is UMA and NUMA. You can visualize these are the number of processors and it is the memory. Okay, so if all the processors have got a common memory, that means it is UMA. If all the processors have got their own memory and then connecting with each other, then it is NUMA, right? Now I guess, have you seen this one? No? Now we are going to understand how exactly a HPC system look like. This is the anatomy of a high performance computer or supercomputer. So this is how your supercomputer look like. This is the architectural diagram. So what happens in that, we have got number of compute nodes which are responsible for computation. Okay, then among those compute nodes, we have got certain number of compute nodes which carry sufficiently large amount of memory as compared to the typical nodes. For example, if these typical nodes are holding, let's say 128 GB of RAM with them, then it is going to have, let's say 512 or 1024 GB of RAM with them. Why? Because they are designed for those applications which requires more memory while execution. So compute nodes are there, but some changes have been done, so that if this situation arises, if the application comes, then we should not fall short of memory. Okay, so these are also compute node, but with more memory. So that's why they are called as storage acceleration. And then we have got accelerated compute nodes. So these are nothing but the same compute node, but now some graphics processing units have been added with them. Okay, so they have got more GPUs with them. So that's why they are being called as accelerated compute node. Then we have got a switch fabric which looks after the interconnection in between these compute nodes. Then thereafter we have got some more compute nodes which have been designated the job of login nodes. Whomsoever want to do work in the supercomputer first need to contact these login nodes. We can only access to this infrastructure with login nodes. That is going to verify your credentials or look after the availability and each and everything. So yesterday you would have come across this login nodes only, where you have done the SSH and got the access of the remaining resources. Okay, then you have got a special file system called as parallel file system. Then you have got a backup mechanism so that the reliability can be offered. And you have got some special nodes called as boot servers or management nodes which look after if there is any fault, then where exactly that fault is and how to boot the overall system, and in case if any new compute node has to be added, then how it has to be added to the system. Okay, so all those things are going to take care by this boot server or the management. So these are the things regarding a HPC system. Is that clear? So if this is clear, that means you know how a supercomputer look like from inside.
What is this red line connection and the blue line?
This is the InfiniBand connection, and that is the optical fiber. Because we want memory access to be as fast as possible. Okay? Because these are number of compute nodes and they are going to carry some tasks, and of course some operations are going to be performed. So there are going to be interconnections, there are going to be some inter-process communication. So that process has to be as fast as possible. So that's why instead of using those typical LAN cables, we use optical fiber cables. And in this case, we have InfiniBand. So there are several other implementations, and we have got other cable network as well. So in case if that get failed, which is primary interconnect, then the secondary interconnect will kick in. Okay?
So, when we see supercomputers, does data processing or execution faster in this components of clustering, which makes that possible,
Which makes that possible. They collectively make that possible.
or the components?
Yeah, that collectively make that possible. It depends what is your application, what is the scale of your application. For example, in your application, you just want to have 50 number of cores. 50 number of cores are sufficient to execute your problem. Then only 50 cores will be utilized. If those 50 cores are accommodated within a single compute node, then only one single compute node will be fired. Let's say you want to have these 1000 CPUs, then maybe 2 compute nodes will come together to serve your request. Like that. Okay, and depends what is the availability of each and compute node, each and every compute node.
Can you tell us what will be done in the
So this is the HPC software stack. So we have got operating system at the bottom, then we have got middleware applications and management tools which look after the file system, provisioning, monitoring, and job scheduling. That is very important. So that look after the job scheduling. So whatever problem you have got, you schedule that application or problem with the help of Slum. That how many nodes you require, what is the input, where to store that output. Okay, so all those things you are going to define with the help of a shell script, and that script is called as Slum. Okay, how many compute nodes you want to have, how many GPUs you want to have, how many HSM you want to have. So you can specify most of the things using Slum. So whenever, if you are telling me, right, that you need to use the supercomputer. So if you want to use that supercomputer, you need to present your problem using the Slum script. Okay, that is the algorithm, that is the data. So all those things have to define the formal script, and then that script will be presented to the HPC system. So whenever the system gets time, it will start executing that script. Then we have got HPC programming tools which look after the performance monitoring and development and applications. So we have already talked about the components of supercomputers. We are going to have processors, memories, interconnects, accelerators, which are graphics processor, then the storage systems, system softwares, application software. So these are again some of the components. Now this is how your supercomputer look like actually. So there are going to be big racks, and in those racks you are going to have these compute nodes, and these compute nodes are going to be placed one by one like this, and then they are going to have the interconnection. So the fastest supercomputer which India is building is the ATAL, and that is going to have the speed of, I guess, in the order of exabyte. They are planning to have the scale of exabyte. Now, in this compute node, this is how a motherboard is going to be. So as I told you initially, so this is the chipset, and in this chipset you can now have how many sockets? 2 sockets. That means how many processors you can put? 2. So we have got some dual in-memory modules which supports the RAM of 1024 GB. So that means in these many slots you can have the number of RAMs till the point this motherboard supports. Okay, so these many RAMs you can attach, and these are the PCI slots, peripheral component interconnect, where you attach the graphical processor or the GPU cards. So how many GPU cards you can attach over here? 2. And you have got 16 data links. So 2 processors you can attach over here. Then this is the layout from the inside of a processor. So you will be having a processor, and in this case our processor has got 2 cores, right? And they may have their own memory called as L1 cache, and then together have got they may have another stack of memory called as L2 cache. And similarly we may have multiple processors, and then they together can come and can run an application, right? Now making use of HPC, again the answer which you wanted. So a team of domain expert and computational expert is needed to develop a HPC application. Until else I won't be able to help you out. You need to tell me, sir, this is the dependent variable. Please don't touch it. Otherwise the whole algorithm will be a problem. So designing or developing HPC FS software, you need to design parallel algorithms, you need to write parallel codes, making use of parallel programming framework. So this is how the things are going to happen when you are trying to develop HPC aware software. And then making use of other applications and workflows like open source things and proprietary softwares. So in short, as I already explained, if you have got a problem, so the domain expert has to come, has to sit, and they have to analyze the code. Even if you run a profiler is a piece of code which will analyze your sequential code and will tell you that this section of code you can run in parallel. It will scan your whole program, it will find out the sections which are running independently. So it will let you know, since these section of code are not dependent, so you can run those sections in parallel. And let's say you have got number of for loops to do certain things in number of iterations. So each and every iteration can be performed by a thread, means a CPU, right? So this is how you can do the things in much faster. And of course, in between there will be some shared variables which are going to be used by each and every iteration. So how exactly you are taking care of that shared variable, that is also a very important thing to take care of. Okay.
Just correct me if I'm wrong. You said basic operations of A and B is of no use when you use quantum computers. Does that suit for supercomputers also?
I just gave you a very simple example that is very much true for supercomputers. Very much true. Why you are going to make the use of supercomputer? You make the use of supercomputer because it comes with a cost. And in supercomputer, fact is very, you can say there is a fact which is very widely known, and that is one can give you supercomputer for free, but the actual cost comes when you try to when you try to manage it. In Hindi we used to say हाथी को खरीदना तो आसान है लेकिन उसे पालना मुश्किल है. It is quite simple to buy an elephant, but it is quite hard to just take care of it. The same thing applies with the HPC. It can do, but why you are wasting so much of power behind to run that HPC?
Then what could be the task for which we can do for supercomputers?
We have discussed number of tasks initially,
Like
where we have
huge
got
data.
large amount of data, where we have got huge space for exploration, right? So those are the applications where we can make the use of HPC. She has got some application where she is facing the need of HPC, right? Even she has got some problems where she need to make the use of HPC. So, more or less, all the AI ML people who make the use of deep learning algorithms and all, they do feel the requirement of some stuff, right? आपने केवल को लगा दिया है, you have just put an algorithm and it is running for days, right? Now these are the parallel algorithms, paradigms, which will come into force in order to run the parallel algorithms. For example, the phase parallel model, in which the parallel program consists of a number of super steps and each has two phases. The first one is called as computation phase and the next one is called interaction phase. So let's say whatever problem you have got, you have decomposed that problem, okay? And then each and every subtask is being done in parallel, and when needed, they are synchronizing. For example, you have got a for loop and you have got number of iterations. All the iterations are executing in parallel, but in between there comes a shared variable which has to be accessed by each and every iteration. So at that place, they will synchronize their activity. And in the context of operating system, we say access to the critical section. Right? That's where the synchronization will come into picture. Why? Because not all the processes can access those resources. There have to be synchronization. Only one at a time will enter that critical section and will complete the job. And when the job is done, the other one will come. Will do. Okay? So that's where this synchronous interaction will come into picture. Apart from that, they are free to do their parallel jobs. Okay? So the computation where the things are independent in nature, they can do in parallel. Where dependency is there, they have to put a barrier and they need to synchronize their activity, and again the same process will keep going on. Is that clear?
Suppose you have a simple algorithm. You can put a very
If dependency is not there,
suppose that job you can submit the job in 1,000 processes. How to fast? With a simple algorithm, you can simple machine run fast. Same job you can put in share with 1,000 processes. How fast it is? Like it will stack on the performance. Small jobs in the complex processes.
okay. So I will try to clarify the doubt which you have got. Here, if we have got 1,000 processors, right, and we are doing a job with the help of 1,000 processors. This is the first thing which you wanted to ask. So in this case, again, you have to look whether creating the parallel solution is a viable decision or not. Because even the parallel computing does come with a cost. Because in this case, you need to create multiple threads. You need to join the results of multiple threads. And that do come with the overhead. So if the task or the job can be performed by a single CPU in the considerable amount of time, then it will be done. Until unless you see the advantage in using the parallel computing or parallel processing, you don't go for that. That is the first thing. Okay. So first you need to analyze, although I have got 1000 processor, if my job is big enough, that can be partitioned into 1000 chunks and can be executed in parallel. Of course, you can have the time analysis. You can see that how much time it is taking, and what if the same thing is being done with a single processor, then what is the time it is taking. So that will help you to analyze whether I should go for the parallel processing or not. By default, each and every or most of the application or most of the programs do not make the use of multiple processors. If a system or workstation has got, let's say, Xeon processor with two processor, and each and every processor, may have, let's say, 32 number of CPUs. So it is not necessary at all that all the processor by default will be doing the parallel computation. They won't do it. You need to tell the computer that you need to use all the CPUs to run this program. Only then it will do. And in some of the graphical applications, they are designed in such a way that they do tell your GPU that now you need to make use of all the CPU cores or all the CUDA cores. Then it runs your graphical applications. Like your high definition movies. Okay, like your high definition movies, because now they have been known as a GPU. Earlier, they were being used for only graphical processing, but now seeing their potential in general applications, they are also being used in number of applications where number of mathematical operations, image processing, and other things are coming into picture. Okay, so did I answer your question?
Yes.
Okay. So first you need to analyze the thing, and it is like, if the thing can be done with a needle, then what is the need of a sword? They have got their own application, right? Where the needle is useful, the sword is needless. Where the sword is useful, where the needle is useless. The same concept is applied if you have a standard application, a standard system, or a HPC system, or a quantum system.
I got an experience, that's why I submitted small jobs in multiprocessors, stuck. A small job submitted in multiprocessors. The process
Yes.
is very slow, suddenly stuck.
No,
But the same
because
thing is submitted in
it
computer.
requires the communication overheads.
Yeah.
It requires the communication overhead. You have got a task, you have divided unnecessarily. For example, it is very general. If you just try to think it by yourself, then you will realize if the task is simple enough, not a big one, and now unnecessarily you have broken that task into number of tasks, then what about the distribution overhead? What about the joining overhead? Until unless the grain size is large enough, that is not going to make any sense. Okay? Should I move further? Now this is another approach where the task is being divided into subtasks, and the moment these subtasks are being executed, then at the end they are being joined, and collectively they are going to produce the final result. So this is called as divide and conquer model, where the parent process divides its workload into its child processes, and child process carry out the work, and then at the end they combine their work, or they merge their work. Then this is the pipeline model. you all already know what we mean by pipelining. So there are a number of instructions that can be executed in parallel. So even that is also one of the way of doing the parallel processing. And then we have got process form model where the master process is responsible to divide the task into the worker nodes, and then the worker nodes carry out the task, and when completed they submit their job to the master node. Okay. So these are the desirable attributes for parallel algorithms. The concurrency should be there, scalability should be there, data locality, modularity. So these are some of the points which will always be there whenever we are trying to run any parallel algorithms. Of course, we want to run the things in parallel or in concurrently. Then it should be scalable. If the volume of the data increases with time, then it should be scalable, right? When writing parallel codes, how to distribute the data to memories, then how to distribute the code to processor, how to organize and synchronize the workflow, optimize the resources requirement by means of efficient algorithms and coding techniques. So whenever we are thinking of writing parallel codes, we need to take care of all these aspects. How we are ensuring that the data is going to be distributed across all the memory nodes, then how we are going to distribute the job among all the processors. Okay, if we have got n number of processors, then how the job is going to be divided. So that we need to take care of. Of course, number of strategies are going to be there. Then how we are organizing the workflow. We have seen several techniques: divide and conquer, okay, process form model, pipeline model, synchronous interaction model. So how the thing is going to be done, that we need to take care. So these are some of the things that need to be take care when we are writing the parallel codes. And these are the frameworks to implement parallel programming model: OpenMP, MPI, and OpenSSC. OpenMP, which works for shared memory computers. Okay, when we have a single system where the processor, where we have got multiple CPUs, and all those CPUs are sharing the same memory space. Okay, and then in MPI we have got multiple memory spaces, right? And in OpenSSC we make the use of GPUs to carry out special tasks. So we are going to see OpenMP in the lab session. So suppose this is summary. Now I would like to show you this one.
The race for the world's fastest supercomputer is on. China held the lead for the last 5 years, but the United States has surged ahead with Summit. It's a $200 million government-funded supercomputer built for Oak Ridge National Laboratory in partnership with IBM and NVIDIA. But what is a supercomputer? Today's supercomputers are comprised of thousands of connected processors, and their speed has grown exponentially over the past few decades. The first supercomputer, released in 1964, was called the CDC 6600. It used a single processor to achieve 3 million calculations per second. While that may sound impressive, it is tens of thousands of times slower than an iPhone.
If you have a smartphone, it is more powerful than the supercomputer that we had back in 1995 doing human genome.
Today, Summit consists of over 36,000 processors from IBM and NVIDIA that can perform 200 quadrillion calculations per second.
What a typical computer will do in 30 years, this machine will do in an hour.
Summit takes up 5,600 square feet of floor space and has nearly 200 miles of cable. It uses 4,000 gallons of water per minute to stay cool and consumes enough power to run 8,000 homes. But why do we need such fast computers?
It has tangible results in terms of how it helps society at large. It will translate into better appliances, better security systems, better delivery of power, more efficient homes. Every aspect of life, it'll change.
Supercomputers are used across all sectors, forecasting weather and climate trends, simulating nuclear tests, performing pharmaceutical research, and cracking encryption keys. Summit is the first supercomputer designed for artificial intelligence applications, and researchers plan to use Summit for AI projects that could identify genetic predispositions to cancer or opioid addiction. By surpassing China, the US has escalated the tech rivalry between the two countries.
There's no question the race is on. But this is not the space race. This is the race to knowledge.
But faster supercomputers are already on the horizon. The European Union, Japan, and China are all developing machines they say will outperform Summit. The next big frontier is exascale computing. That is, computers that can perform 1 billion times 1 billion calculations per second.
The use of this machine is only going to be limited by the imagination of the scientists who will have access to this machine.
Hey there, thanks for checking out CSC on YouTube. Be sure to subscribe to stay up to date on all of the data.
So you studied exascale supercomputer?
Yes, no, this is in the scale of petabytes. Peta. Yes, peta. And that has been ranked, I guess, 8th or 9th in the top 500 lists. So I thought I should keep this video so that you can have the idea how exactly the supercomputer look like and how the operations are being done and what are their significance. So that's what we have seen in that video. And you will be quite amazed to know now the people are thinking to build the nuclear reactor to power the supercomputer. So that are the power requirement of the supercomputer. So if this summit was in the need of, means if the summit requires the power which can power the 8,000 homes, which is currently on 8th position, 9th position, what about the frontier supercomputer, which is ranked 1? And what about the system or supercomputer which is about to build, which is going to be 9 times than the frontier computer? Special your substation station are going to be there. CDAC has done the extraordinary effort to keep that system running. Even a single second power down cannot be tolerated.
If this is the case for building a supercomputer, what it could be for quantum computers in terms of time?
Yes, there are a number of hardware challenges. So that's why India is still striving forward to build a quantum computer because it poses a lot of challenges.
In quantum Shaw's and Grover's breaks the RSA encryption techniques. So here in the video they mentioned that supercomputers also cracking encryptions.
Yes, they are cracking. So for that we have got the concept called sessions and all. If you are trying to do the banking transactions, then your session is of 1 minute or 2 minutes, 8 minutes. The moment you create another session, then another key is being generated. Okay, this is first thing because we have that session wise. Of course, if we are making the use of supercomputers, then that can be done, but even that is taking considerable amount of time. Okay, for example, if your supercomputer is taking 5 minutes of time and your session is live for 1 minute, your job is done. However, now the problem is how you are making the use of supercomputer to get that job done. First you need to see that how that is possible practically. For example, you have got certain packets with you, and now you will need to break this particular packet with the supercomputer. Now you tell me how you are going to do that. So in order to use the supercomputer, a lot of protocols are there, a lot of processes there. It is not a straightforward job. It is not like a typical computer where we have the session, we just capture the session, we capture data, and we have got something, and then we applied some cryptanalysis techniques or differential cryptanalysis techniques to get the things done. It is not like that. Okay. And what was the other question? That was it?
Cracking encryption keys.
Yeah, so for that we are working on post-quantum cryptographic techniques. Okay, so yeah, that has been worked, and we have quantum key distribution and all the techniques.
But what my question is, if supercomputers and quantum computers are going to break the encryption keys, what is the purpose of building it? Anyway, it's not going to provide this secure communication for this. It's going to break the keys.
No, it is going to break, but that is one application. You are looking one side that you want to break this security mechanism. What about the other applications which
Of handling data.
you are thinking that what can be the misuse of it? But I am asking what are the uses of it? Okay, so this is one thing. And the other thing is, it is not a straightforward task to make the use of HPC. Whatever thing you have got, you need to schedule it properly. You need to get this slot of it. Only then you can make use of HPC system. If you submit your job today, it is very much possible after 1 month and so you get this slot. Okay, and there are very rare applications, and for which the dedicated supercomputers have been built. For example, here in what is the forecast department which look after meteorology. So that department has got their own supercomputer. Okay, and that is dedicatedly meant for that only. So whatever data it has got directly, it is being executed or analyzed by the supercomputer. Okay, but in order to have this security, of course, one can have powerful systems and one can look forward. But for those, again, will look forward that what is our application. If we want to have our application more secure, then of course we are going to use some other advanced technique like ECC, elliptic curve cryptography, which are quite hard to do. So it depends. If we are just doing our Bluetooth communication or some small scale communication where the sensitivity of application is not that much, then you can use simple symmetric applications or asymmetric applications, right? Like RSA. If in case you have got an application which has to be more secure, then the technique like ECC can be utilized with the much better key size. Okay, and of course, the moment we have the realization of quantum computers, then we have to think of having these post-quantum cryptography techniques. That time it will be needed. Any other question? Anyway, I will be with you in the next session as well. So should we conclude the session here?
Do we have the access? Do we get the access to for the supercomputer processing for that?
Supercomputer or quantum computer?
For an educational institute, so we want to do some.
Supercomputer.
Yes.
For that, you can mail to NSM, National Supercomputing people, and they will scrutinize your application and they may give you the access. So, since India is running a national mission on supercomputers, so they are promoting, they are advertising their hardware, their infrastructure, so that the
we get simulation only, right? Simulation. Right?
Simulation. You need to done the computation.
Yeah.
You have an algorithm, and that the algorithm takes days of time, and you do not wait. You do not want to wait for that long. So what you can do, you can just make the use of HPC system. So rather than having the result in 1 month of time, why don't you have the result in, let's say, 5 minutes or 10 minutes? Okay, so that is the advantage. other doubt? Question?
IT has such a
get the spots from the websites.
but still it has developed quantum computer.
The answer is same.
What is the quantum advantage over this?
The answer is same because all the things cannot be done in a faster way if we take HPC into consideration. It is doing things fast, that is fine, but quantum advantage is something else. That computing paradigm is it is going to give you exponential speed. If you are able to create or write the quantum algorithm which leverages the advantage of quantum computing, then only you have the benefit. Okay, so let's say we have got 20 applications or 100 applications, and there are 5 such applications for which the quantum algorithms exist. Then you can make use of quantum computers. For rest, 95, still you will feel that I need HP systems. Like
Quantum computing is ENIAC stage.
quantum computing
The ENIAC stage.
in
ENIAC is first like
what is the current status?
first computer is ENIAC, right? Same stage is now quantum.
As of now, that has been the quite a thing to discuss, and a lot of countries have taken up this job on the most priority basis. Even for that reason only, India has launched national mission on quantum computing as well, because they have identified the areas where most of the countries in the world are doing the research. So supercomputer is one such area, quantum computers are one such area, AI is another area. That's why you can see that the government of India have created the national missions for this. They have allocated around 6,000 to 7,000 crores for supercomputers, for quantum computers.
So isn't quantum computing is like where we use the network instead of what is the network? I'm not much aware of the network system which we are using right now, but from what I heard, it is going to be quantum computers are going to replace that network system. Right? For that only, it's being built in every country.
It's not totally true. It's not totally.
Because some research says that.
I give you the example of needle and sword. So whenever you have the doubt, just remember this. So you will get your answer. Okay, and apart from that, one more thing which again I will add, you need to have the algorithm first. Quantum algorithm. Only then you can leverage the advantage of quantum computer. Otherwise not.
Because it has been I guess I have been in a seminar where they have been talking about quantum entanglement and how the
It is
data
like
which cannot be happened in
it is like, in a simple word, you have got a railway train from Chennai to Delhi. Until unless you have train, you can't use it. You can't use it for bus or ships and all. Yeah, please. Your question was?
It's like we have high secure data which we need to transfer through our networks. So those can be breached. And those happened when our Mars mission or Mars mission. So our Mars rover used to send the data to us. So it can be breached easily. So per se, the professor told like if there is a quantum technology in it, that the breach cannot happen because it's based on frequency. So it can't be breached. So isn't it like for a network?
That is another aspect. That is called as secure quantum communication. That is secure quantum communication. Now we are talking about the quantum communication.
Single electron itself is difficult to entangle. So far, technology is not as much developed.
It is like a frequency mapping. It is like a frequency mapping. Like
both are paired spins. Then you can separate out in spooky distance. pairs. Only we can entangle. It's not like everyone can entangle each other.
That's why they have other source on the other side. We have one source from our side.
So it will be entangled only. You have to be
two pairs.
So that is difficult to identify. It's a big stage.
They claim that quantum does everything, but still they are using the conventional methods.
They are using because
Even government investments
And also that's a process of only like
it needs to be matured.
storing
It's in developing stages. So the moment the things have been matured, only then people will start using
It was
it.
sent by a professor, like scientist from Manipur, Bhattacharya.
So when do you have next session?
About this, we are spin-off.
From 2:30?
And this session, like
From 2 to 2:30.
we are building servers everywhere, right? So if we are building servers, instead of the pollution is above environment, like proposals. So in order to minimize that, they are planning to put a server in each and every location, so that we don't have to go for the space for communication. We can use the quantum. Can we have the artificial normal?
Anyway,
That also can be done in a very simple way.
I saw that many of you are interested in quantum computing. So we are going to float one workshop in NIT Raipur in next month. So if you guys are interested, then you can join that workshop.
Hybrid or
Hybrid.
One more question.
Yeah.
Sir, which is a breed of machines?
That I have not explored, so I can't answer you. But the people are trying to build the green solution in HPC as well. I'm not sure about quantum. But in HPC, they have surely expressed their interest that how to build HPC solution which exhibit less amount of CO2 and all.
CO2 emissions huge.
So that is the concern.
Consuming too much of power.
In quantum, I have not explored that part because still we do not have all those things, and still the world is working. So now their focus is to first build it, then they will see what are the other things to take care of. Because they are quite small in. Yes. I work with Param Utkarsh.